So today and the beginning of next week, we will complete the first part of our journey. And you're probably bewildered because this is some kind of physics course and it's all drawings and God knows what. And it goes against the training of a physicist. So what we did in the first part of the course is we tried to popularize some geometry. And in a sense, it's an ode to curiosity. Because all the ideas which are important today were just done out of curiosity. You know, nothing that we do was NSF or NIH sponsor-directed research. And in the long run, you know, this is the amazing stuff. So the fundamental idea that underpins it all is that after a long time between Leibniz and Poincaré, the focus was on being a virtuoso in analytic solutions of very complicated integrals, typically in celestial mechanics and fluid mechanics and electromagnetism, etc. And that's all they could do. I mean, it was totally amazing. It was all they could do. And Poincaré was a person who understood that you must have a feeling for qualitative theory of differential equations of flows. And that's what we have been doing up to now and do it also today and a little bit later. So what I'm presenting is a revision of Poincaré and Smale in the 60s. Smale is still alive, still very active. And you know, it's puzzling because it looks like pictures. It looks useless to you, and drawings and cartoons, and you're working people, you don't have use for it. But calculations are to machine precision. And what's happened between them and us is that they developed a qualitative theory, but we can actually implement it. We are lucky to be here in time where we have a tool, and that's just a tool, that says that if I understand the qualitative theory of dynamics of how things evolve in time, and I can actually compute this. So these pictures are extremely powerful. I mean, when you implement them, you know, they're all to machine precision. They give predictions. Often you don't care about machine precision, but if you apply this, I won't cover this in this course because there will be a 2-semester course in quantum mechanics and quantum field theory. When you use these ideas, you compute spectra of helia, so, you know, things that are measured with very, very high accuracy. Here we insist on precision when we implement this because the theory turns out when you have simple rules, simple laws, how things should behave, but long-time behavior is complicated, the way that we will understand it will in terms of classifying invariant structures that characterize the thing that looks very complicated. You know, our intuition is that you have a very simple, like we have a parabola, or even the tent map I showed last day. So how complicated can that be? Yes. So there must be some intelligent way of using the information that the law is simple and projecting that information beyond the horizon, which is called a point of time, but beyond the horizon where numerical work could get you without thinking. So our strategy was so far to define another picture, define all possible things, enumerate them, so that's called state space. And unless you do that, you can't do anything. And then describe the law which tells us how things move around the state space. So that's the definition of dynamics in this course. There are more refined definitions, but this should work for us. And we did this by first looking at trajectories. An important thing is that we discovered there were sets of invariant trajectories. There were equilibria, And no matter how complicated the motion is, the mathematical solution, which is equilibrium, is equilibrium. It's not complicated at all. That we found that there were recurrent motions, which were a little bit like what people always hope to find when they were doing analytic integrals in celestial mechanics. Something where you can describe in a very simple way motion as motion on the circles. But they turn out to be unstable, isolated, and as you will see, there's a very large number of them, infinite number. So these are periodic orbits. Then there are other structures. And importance of this object is that they have temporal dynamics, even though they are invariant as a sets. So they sit in this space and just sit in some part of the subspace, and they don't know what's happening every place else. They start capturing the temporal evolution because the points are marching along them. And there is a list that is very short in practice because we actually don't know how to control most of these objects. So by now we have mastered basically equilibrium, periodic orbits, and some Torah, but the general classification of this motion eludes us. So that was the first thing. What happens to point? What happens to a mathematically infinitely precise thing? But there are no points for many reasons. There are only fuzzy objects, which is our best specification. And that could be because we have finite numerical precision, or we don't understand the law. So we have approximate law, like we have Newton's equations instead of the correct ones. Or we live in a world that are perturbations that we don't control. So something happens, Professor Goldman exits the lab and the acoustic waves propagate in here. And there is no control of it. So the things are really not sharp. And that's totally different. So what happens, the moment that happens, the world, we have gone from idealized world of determinism to statistical mechanics, which is fully deterministic. The laws are deterministic, but the way thinking about it is very different. You have to start thinking about distributions. And that'll be the second part of this course, which will start probably on Thursday next week from now. But what we found was that it was very useful to understand transverse behaviors. And that led to an unfortunate, but either very ugly or very beautiful, depending how you feel about diversion in thinking about symmetries. So there were here symmetries. So it often happens that the laws that we look at, the phenomena they observe, they look like in kaleidoscope. There's something like that, and there is something like that, there is something like that, and there is something like that. And that's beautiful, but it turns out it interferes with understanding. So I made a little digression, which required actually writing formulas. I apologize, but this is absolutely necessary because one has to understand the global dynamics of what happens, at least to neighborhoods, bunches of co-traveling, fellow travelers. It's absolutely essential to go into Poincaré section plus slice, which is problem set of this week. And in that world, all the motions that had to do with marginal directions in which things don't really change, so everybody who belongs to a marginal manifold is just a different placement of the same shape, and start discussing what happens in this transverse space. So that is totally necessary already on the level of this thing. And what we have done now for a week, and I'll finish doing today, is that once we understand this, we can start in a very precise way with the local properties of the flows and find the global properties, and no night fishing is needed. This can be done by thinking your problem through. It's not easy, but the other thing just doesn't work. And that enables us now to think of the state space, which was in the beginning just lots of points connected in some very obscure way, to think of it as a smaller space. So here is my phase space. And here is a smaller space which you can write in various ways, but basically what you do is you identify all physically same things under the symmetry group, which could be discrete, continuous, whatever, but it's just a group of all coordinate changes that identify objects which are physically the same, have the same shape or same energy or whatever. All properties are same modulo coordinate transformation, and actually also want to quotient out the time. You did that by Poincaré sections, and it's this space which is not much smaller than the original space. So original space can be any dimension. If you're looking at systems described by partial differential equation, original space is infinite dimension because it's function space. It's every slightly different function is a point in it. Or if you do it the way we do this as a set of coupled ODEs, it's lots of ordinary differential equations coupled, Fourier modes coupled by nonlinear terms, etc. And this space now gets reduced only by one dimension for time and few dimensions for symmetry group, depending on the symmetry group is. But what's captured now in this space is the way that you can leave a neighborhood of, one fixed point or one periodic orbit or one relative periodic orbit or one torus or God knows what, but you have quotiented all that stuff out. And how you actually get from there to some other neighborhood, which has its own invariant thing. And there are things that I'll try to explain today called homoclinic connections, etc. But there are invariant ways to get from here to there. And the power of that description is that it's invariant. No matter who does it, where does it, under what coordinates does it, you'll get the same result. And you'll capture the essence of the dynamics in this way. So I'll just, fill in a few more details. It's work, and there is no way out of it because nonlinear dynamics is not simple. But it's systematic. So if you have a problem, you'll have to work in a different way on every problem, and maybe you'll discover lots of exciting things that are missing from this exposition. But it's a way to do this. So if you find out that you're in a situation where everything looks unstable locally, that doesn't mean that the world globally is unstable. It just means that individual trajectories cannot be predicted with accuracy beyond some time horizon. But it turns out, which will be obvious in second part of the course, that the thing that you really have to think about, which is likelihoods of being transported from someplace to someplace by dynamics, it turns out to be very robust. So while things fall apart on one point level, they actually become very stable on the level of densities of points. So there'll be a dual picture, which makes it actually very easy to describe long-time behaviors once you understand what they are. And the strategy that we started explaining last time, and I will now make it a little bit more specific, is to explore how is it that you leave a neighborhood of one of your invariant solutions, which you control to arbitrary precision. For example, if you find an equilibrium, it's there for all times, infinite or periodic orbit. If it repeats in 1 second, it'll also repeat in 1 millennium, as long as the system hasn't changed. So the key bridge between local and global stuff are stable manifolds. So if I draw a picture, what I have in mind is that if I have a trajectory and I start in its neighborhood, what will happen in finite time, that neighborhood will deform. And I'm drawing cigars. I really shouldn't do that. I should be drawing parallelepipeds, but they're uglier, so I'll continue drawing cigars. And that local information, we know how it works, because if you start with some deviation at time 0, we know that's the Jacobian matrix. That's totally computable from our laws, if this is a theoretical calculation. So we know what that thing does. But now we can do something bolder. So suppose that this is actually living on a periodic orbit. What we have learned very early in the course is that to linear approximation, the set of ratios of the evaluated on periodic orbit, which is various dxi's, dxj's, original ones over the ones that come back, and in a small distance limit, infinitesimal limit, that's called Jacobian. We actually know that that's invariant in the sense that if we compute the multipliers, Floquet multipliers for this thing, there'll be a bunch of them that'll be expanding, there'll be a bunch of them that we have eliminated. And that's why we made this long detour in sections and slices. So they're expanding ones, and there'll be a bunch of them that are contracting. And these things are invariant under all smooth coordinate changes. So the profound and deep property of the orbit. Now, the eigenvectors are not invariant because they depend on our coordinates. They depend on how we place this thing into the state space. What is our coordinates in the state space? But associated with every one of these guys are expanding, contract. So expanding are these ones, contracting are the ones that make neighborhood thinner. there's a set of eigenvectors which depends how we do this, but once we choose the coordinates, they're well defined, and they're defined any place on the orbit. So you can transport them, and when they come back, they'll align themselves with the original eigenvector. So there's some kind of natural rotating frame for this thing. And we can use them to start building our global chart of all possible things. Now, I'm not totally happy because it's always the same thing. When you get down to work, you have to put it in coordinates. And even though the concept is more beautiful, the coordinates are not. So there you are. But the main thing about these guys is that they provide a bridge between, local and global. And the way they do this is that you can define stable, unstable manifolds, and we can define them as sets of points. So stable manifold is sets of all points in the entire state space, such that if I measure the distance from the equilibrium point, so a point like that, actually I don't measure the distance, I just see how the map goes, and that's important. This goes to 0 as t goes to 0. So what that means is that when I look at, for example, this periodic point in Poincaré section, there is a whole world out of there whose dimension depends on number of stable dimensions in a problem. So we are in million dimensions, but there are, let's say 7 stable dimensions. That would be a bad situation. Okay, we are in 10 dimensions and there are 7 stable directions. Then this manifold, this set of points will be 7-dimensional, and they'll have a property that if I just pick any point here, it will move, and at infinite time you'll land at the equilibrium point. So, what do you say?
As t goes to infinity?
T goes to infinity.
Right.
This is much better, thanks. So associated with every fixed point in the Poincaré section, there is a whole world out of there. But it's very small compared to dimensionality of the whole problem, where everybody falls in. But because by our construction, there are either expanding or contracting eigenvalues and no marginal eigenvalues, there is another manifold which is called the unstable manifold. It's a set of all points which, if you look at the past, so we look where we came from, that goes to 0 as t goes to infinity. So that means that these things that as they went forward in time, they were going in expanding directions. If we go backwards in time, what used to expand now contracts, and it's same definition, just with the time reversed. So that there is another manifold which is the points that forward in time will run away, but they all originated in an infinitesimal neighborhood of our fixed point. And this stable unstable manifold for each point actually partitions the space, because they have their dimension is the full dimension of the space. Now, how do we get grip? This is a mathematical definition, and it's a bit useless, because if you just try to do this as an experiment, you'll take lots of points and they'll all run away. Because, it has to be on a small manifold which is curved, complicated, etc., that at infinite time, which you don't control numerically, lands on this thing. So you need a more useful definition. And you observe that actually there is a natural coordinate system provided by dynamics. So as you live in this Poincaré section, you have locally some number of stable eigenvectors, these guys here. And they're the little corner of this complicated manifold that's curved all over the place. In the neighborhood of the fixed point, the linear neighborhood, just a nice little neighborhood spanned by tangent vectors. And there is some other set of directions, which are the eigenvectors, unstable ones. So in a little neighborhood here you have total control. So now can you project your total control of your little neighborhood, of your little family, into global control of everything? And there is a very intuitive, nice way to do it, which is to realize that while this is a hypersurface, which is complicated, etc., in some sense it has edges, because in each one of these directions, if you take some point close by, it'll march away on a line which is within the unstable manifold. So it'll be one-dimensional line. So it'll be like an edge of your domain. Because these vectors, which are not usually orthogonal, span some kind of parallelepiped, and you can actually sort of expand that parallelepiped projected into the space by going forward in time. So you can define lines, or if you have complex eigenvectors planes, I'll do this in a second, which kind of give you a thing that locally spans, because locally they're linear vector space, so locally it spans everybody who's unstable, but it also gives you description globally where the unstable volume will be, even though it's going to be curvilinear and not so sweet. And that you do then by looking at your eigenvectors. And the expanding ones will satisfy the Jacobian at time t is a multiplier e to the j of the thing evaluated at your equilibrium point. So that defines, and those things you already have. And in next lecture we'll need them very badly because they're very essential in finding where the equilibrium periodic orbits are. Solving this linear equation helps us a great deal. And if this is larger in magnitude than 1, it's expanding. If it's smaller than 1, so now I've switched my colors. It's smaller than 1, it's contracting. And for people who are watching the camera, this says expanding, this says contracting, even though it's off the screen.
It should be greater than 1. Is it greater than 0?
Absolutely. So the multipliers are either greater or smaller than 1. The exponents are greater or smaller than 0, they're logarithms. And now how do you use this information in practice? I should probably mention the complex pair because that might find it confusing, but or there could be a pair of eigenvectors which, when we make a list, this index tends to be from the most expanding to least expanding. And if you have complex eigenvectors, then the eigenvectors come as complex pairs, and the multipliers come as complex pairs. Meaning the magnitude doesn't change, but the imaginary part of multiplier changes. So that's a complex case. And I won't cover it here, but if you have some other symmetry, like if you have symplectic symmetry of Hamiltonian systems of mechanics, there could be further quadruplets and stuff like that. But if you don't have any other symmetries, this is a real matrix has either real or complex pair eigenvalues, and that's all there is to it. So how do you now use this information?
Shouldn't lambda also have a superscript?
It should be, yeah, so it corresponds to the same eigenvector and eigenvalue count is the same pair. Anyway, I don't know where to stick all these letters because there is a time index, there is a spatial coordinate index, there is the eigenvalue index, etc. So the notation tends to get confused every so often. But basically, if I put it in a bracket, it's counting the eigenvalues. And if I leave this bracket out or parentheses, I usually mean the coordinate label in d dimension, ith component of a vector in d dimensions. So what you do is you just take one point and we'll just take one unstable direction as an example. In your state space you have a point Q, it's in many dimensions, and from it there's an eigenvector. Tangent space is the same dimension as space, so if this is a 37-dimensional space, this is a 37-dimensional vector. I draw it, it's not one dimensional, it's 37, it's the same dimension. Then what you do is you say, you play with it and get some sense of how far do you have to go before the nonlinearity of system becomes important. Your equations tend to be nonlinear, and what it'll mean is that if I take some point close to this, and I let systems iterate it. Remember in the Poincaré section, so it'll come back. And if you're close to fixed point, it'll come close to fixed point because it's unstable every time it'll come out a little bit further. And if you notice that there's some curvature in the space, it means nonlinearity has kicked in. So I don't have a good measure. You have to check it in every system, but typically your equations are good to maybe, a computer works on 10 digits, but the important objects of size 1. So if you take something sufficiently close, it'll march first linearly and then it'll start marching a set of points going there. Now, if you take another point in between, by topology it's on a line, so it has to stay there. If you take 100 points, then it'll look like an interval. And if you do it so cleverly that the first point of this interval maps at the end of the interval in one iteration, so one Poincaré map of xn lands you here at xn plus 1, then what will happen, that the entire interval will get mapped onto itself. So the next time it'll also be an interval, which to naked eye will look as a line because it has lots of points in it. But it'll be stretched because the distances are multiplied. Anything along here is multiplied, any deviation by the linear thing, by lambda. So if this is in your, whatever your measures are, this is 10 to the minus 10 in distance. This thing will be your multiplier, expanding multiplier, I don't know which one. Let's say the first one, the most expanding one, times your delta x. So there'll be a bigger interval. Then it'll become bigger still. Then it'll become bigger still. And pretty soon you'll start seeing this is actually 100 points because this is expanding itself.
Can you explain again what are we doing?
We are learning how to compute unstable manifold on a computer because there's no analytic formula for them ever. So, how do you actually see what unstable manifold is? An unstable manifold is a big volume because if there are 3 expanding directions, it's a 3-dimensional manifold. So for us, it's very hard to draw 3-dimensional things deforming. But we are so lucky that there is a natural coordinate system, which are the eigenvectors. So they work like the edges of the unstable. There's a volume. It's a parallelepiped in linear approximation. So if you start with a little parallelepiped, it's not a cube because angles are never orthogonal for these Jacobians. These are matrices that never have orthogonal frames. This probability one, they just deform stuff. So you want to see how this parallelepiped is growing as you go further in time because all points are running away within the unstable manifold. And one way to do it is to figure out what the edges do. So now we are computing one of the edges. And that edge is a line. And that edge is a curved line in a space because close to equilibrium point, linear dynamics is good. We do not know that there are all kinds of other objects in a state space. But when you get a little bit further away, there's actually another point here, x cubed pi. And that one is going to mangle our flow because it has a different dynamics in its own neighborhood. So the unstable manifold will curve. And I'm telling you, you can, for your problem, you can actually draw a picture of it. See, this is a line. So even though you're in 46 dimensions and you have no visualization in 46 dimensions, you can draw a point and see what it looks like in any 2 or 3 coordinates that you chose. And you can also see what a line looks in any 3 coordinates. So even though you can't see these things, you can see quite a bit because
It's still a two-dimensional line.
it's one dimension, just a line. You know, it was a vector because you know, it's the edge of the thing. So here is my deformed surface. One vector points this way, one vector points this way. And now I'm just trying to figure out how this curved thing is going to look like here and how it'll look like there. Yeah?
But this curve has no significance in the global distance.
Ah, good question. That's why we want it, because that's our invariant guide. That's you know, native guide from local neighborhood to the big global world. And it has significance because the invariant solution is invariant solutions in any coordinates, no matter how you do this. So no matter who does it where, they'll find the same invariant solution. There'll be a different position in their coordinates. It'll be same invariant solution.
So for that, you have to find the same point in the other coordinate.
Yeah, so in other coordinates there'll be this point. In other coordinates there'll be this vector, which is solution of the eigenvalue equation, because this matrix is defined in the coordinate set and this vector is in given coordinates. So when we go to new coordinates, this vector will change to some other vector. And we discussed this very early in the beginning, that's called smooth conjugacy, how you get it. But the stretching rate is invariant. Stretching rate doesn't depend because the multipliers are properties only of dynamics and not of coordinate representation.
But at different points, those eigenvalues will change? Or
No. Oh, no, every solution has different set of eigenvalues. So their properties.
Subtracting later? Or?
Right now we are starting in a neighborhood where there is a unique set of eigenvalues, and we're using those to start sailing into the big world. But we're not doing it blindly. We're doing it on invariant curve, which will be invariant curve for everybody else as well, no matter how they, you know, stretch their world and plot it. They've all agreed that this is a continuation of the first unstable direction in neighborhood of this thing. Now, if this invariant curve goes into neighborhood of the second thing, or maybe even hits the second equilibrium, then no matter how I look at it, that's a topological property of the flow. So that's a very robust thing. So even though my pictures of it might differ from person to person, the statement that the two neighborhoods are connected by an invariant curve will be an invariant statement. And the statement how I get from one to the other one will be also invariant, because this curve will be a unique curve. I will find the same you know, flight time between them, if you wish, because that's controlled by these eigenvalues. But now this curve goes off, and what this curve does, unstable manifold, so what's very important is to know, yeah, here you start, but you have to be wise enough to know when to stop. Because if you actually just keep using your dynamical system and iterating, this turns out to be a curve like any other curve. In long time, usually it's an ergodic trajectory. And it's doing what every ergodic trajectory does, it's exploring the neighborhood, it goes all over the place. So if you don't stop someplace, you will just start filling out whole state space with this curve. And you will not be any wiser than just running any random point. Yes?
Where do you find stable and unstable manifolds in respect to a fixed point?
Yeah, so
they are defined locally, only in a neighborhood of some fixed point.
Yeah, so I'm telling you, locally we have very clear definition, but they have unique continuation. See, this is a unique continuation of the local neighborhood, globally.
Yes, but for another fixed point...
They look different.
They look different.
Yeah.
So at each point, there's different set of vectors, which is a smooth deformation from the starting point.
Yeah.
The eigenvalues may change, but it's a single valued thing we're looking at.
It's a unique trajectory,
Deterministic trajectory.
and no matter how you change the coordinates, we can go back and forth and it'll be the same trajectory. So the continuation of the linear neighborhood is unique. There are no three curves.
Continuation is unique, but the set of vectors and the eigenvalues change along the curve.
It definitely changes along the curve. And okay, I'll answer in a second, but let me just say what the strategy is. So strategies that we have figured out linearized neighborhood of this point, call it XQ, linearized neighborhood of some periodic point. This is all in Poincare sections, so they're all morally fixed points. And another one, X, P1, P2. And we want to put this picture together. And I'm now, so locally we have very good maps. Linearized tangent space is really good. But globally, what are we going to do? Now I'm telling you, there is a smart way to do this. You put lots of little charts and put the shortest connections between them, and then you control everything. Go ahead, Pavel.
We define these manifolds only for points, for fixed points. We can define them for periodic orbits.
Yeah, periodic orbit, when reduced to Poincare section, is a set of periodic points. And each periodic point is a fixed point of the nth iterate of the map. So if you understand how to analyze one fixed point, the same methodology works for all periodic orbits. Because they're just different maps, but once you have figured it out, you know how to do it for all. So that's the idea. And that's why we had to go slice and cut, etc. Once we have reduced dynamics to just the dynamics of a fixed point, then we have machinery that describes all these invariant sets, even though there might be tora, etc. in a full state space. Yeah.
So when you're shooting along this line, at each point you're going to have a new set of eigenvalues and eigendirections. How do you pick the correct one? If you got for 4 unstable?
We won't do that. We will not. We will only compute eigenvalues of invariant objects, which are stationary, like periodic points. They're stationary under nth iterate of the. And this we will only use to have topologically invariant way of connecting the neighborhoods. So there is no particular meaning. If I compute Jacobian on this trajectory for some finite time, it'll have its vectors and eigenvectors. But they don't have any invariant meaning, because only thing that have invariant meaning are the eigenvectors and eigenvalues computed on compact sets on periodic orbits or equilibria. Now that we showed first. So there are two things. There is one that we can do, which is on any compact set we can compute its eigenvalues and eigenvalues. Now if you're a mathematician, you can also do it in infinite time. So that's called Osseledek theory of Lyapunov exponents. So infinite time orbit is also an invariant orbit. It's just that it's in a gleam in mathematician's eye. We cannot control it at all. So we can't do any calculations on it. So we have a systematic procedure that we calculate longer and longer orbits. For them, we know what we are doing. Yeah.
So for connecting two neighborhoods, we require that the trajectory should be along an eigenvector for both the neighborhoods, the same trajectory.
It'll be a little more complicated, so I'll try to do it in few steps. But first thing I want to say is that I just want to tell you, don't go very far. Just don't go very far, because whoever goes very far will find himself or herself running around the state space just like any other stupid trajectory. Any ergodic trajectory just runs around and you can't make sense of it. So all I want to say is that when you have a linear neighborhood, there is a way, so I put a picture actually in the book, there is a way of going out of the linear neighborhood and still have a nice neighborhood. It's just, like a cup. It's curved, but it's smooth and nice. But at some point that has to fail, because at some point you'll start hitting obstructions of other neighborhoods. And they are different, and they won't let you do this. They'll make you twirl and twist, etc. So what happens in the systems that I'm familiar with is you go for a while, and then you hit some kind of wall. So Rosler was a very good example. You went around, and then you discover that you're folding, and you can't go further. So these unimodal maps, for example, also. So what happens with this trajectory when you plot it, you'll discover that you have had some kind of wall and suddenly starts turning. And it does whatever it does onward. And now my advice is that you stop here. There are ways of defining the turning points well. I mean, basically, this is a curve and has curvature. And when it starts turning very quickly, it's like a mechanical object experiencing strong acceleration. It suddenly has to go back. And if you look forward in time, there are ways of defining it better. But basically, there is a part of the neighborhood that's nice neighborhood still, even though it's curved. And you can use these unstable manifolds to delineate that good neighborhood. So it means that you can make your chart bigger. So instead of just being a plane, it's some curved surface. And you can make the other chart bigger. So you started with infinitesimal information. So you had no idea how to go to your distant relatives or even enemies. But now you can experiment and you can see whether the neighborhoods intersect. Which means that if the neighborhoods are intersecting, then I might be able to make a nice connection and continue in the next neighborhood. So that's kind of general strategy of what you want to do. So
we are assuming here that in the coordinate transformation, this manifold won't deform much.
It can deform very much because if you plot the same manifold in polar coordinates and Cartesian, it might look very different because something close to the z-axis might stretch. It's like Mercator projection versus some other cartography projection. So visually they might stretch. But if there is a railroad from Moscow to Novosibirsk, it'll be there on every, even though it might look 1,000 miles longer or look very short depending on your projection, but topology will remain the same. So if you're lucky, and I won't discuss this very much, but you can be lucky, it might turn out that you can find a particular line in this, see this, you're in part of your volume here. I'm just drawing one edge of it. But there could be a particular line that starts here and ends exactly at the other point. So basically, I'm here and I have my gun and I can shoot in unstable directions. If I do it in stable directions, I shoot myself. So I shoot in unstable directions. So something goes out, whoop, and I'm in 30 dimensions, 100,000 dimensions. If I'm in a plane, I have a good chance of hitting a point. If I'm in a three-dimensional volume, it's a little bit harder. I throw a boomerang, it's not so easy. The higher dimension, it's impossible to hit a point. Yeah. You can hit the volume, but hitting a point gets very hard. So shooting a high dimension seems extremely hard. So it seems it would be impossible to find a direction where I shoot in this neighborhood, space is curved and it goes down, and it hits exactly the other point. However, it turns out it could be quite possible because this guy has a stable manifold which sucks up the whole volume of points. So if I can just somehow get myself into the stable manifold, the other guy, which is much easier because stable manifold is the dimension, it's a big dimension because the whole space is divided in the number of unstable directions and number of stable directions. So if I have one unstable but he has 9 stable directions, it might be very easy to fall into that hole. And that's an insight due to Poincaré again, which is called heteroclinic. Hetero meaning different. If I go from one point to another point and I hit the another point, then I have a connection between 2 different points. So I don't know what clinic means, but this is a heteroclinic connection. And if I have a fixed point and I shoot along the unstable direction, and I manage to fall into the stable manifold. So I shoot along here, do something, and manage to come back along the stable direction. That's called homoclinic. So that says that if I'm clever enough, I might be able to connect these neighborhoods exactly, invariantly, topologically connected. And once they're topologically connected, there's no way to disconnect them. Because once you have a curve going from one neighborhood to the other one, no matter how you change your coordinates, that curve has to be there unless you destroy the continuity of space. But that's a bad coordinate change. So that's the way you can go from the local stability using unstable manifold and start constructing a global structure that you can see because there are points and there are lines and it's embedded in lots of dimensions, but that you can see. And that guarantees that if I'm this neighborhood, I have a likelihood to visit another neighborhood. Because if I have one heteroclinic connection going from this neighborhood, then there is a neighborhood of these guys that follows it for the time that I want to follow it. So this starts enabling me to construct a chart saying, this is a big world, there's Japan, China, but if I go this way, I end up in China, and if I go that way, I end up in Atlanta or whatever. And the set of these mappings that I have is topologically invariant, and they connect invariant objects which have invariant properties, like they have invariant shearing and stretching rates in the neighborhoods. So that's good news. Now there are bad news. And I'm about 2 minds about the good and bad news. You know these heteroclinic connections already, because if you're playing some kind of game on a curved surface, you know that if you send the ball just the right speed and angle, it might go to the top of a hill and stay there. But it'll take infinite time. So you might be able to do it because at the top of a hill has 0 velocity and it's a smooth kind of thing. So if you overshoot at the top of the hill, it'll speed through at finite time. If you undershoot, it'll go and come back. But when you're exactly hitting it, it'll slow down and it'll take infinite time to get there. So in practice, me and my colleagues on 3rd and 5th floor like the idea of heteroclinic connections, being able to get from here to there. But we're having lots of trouble of understanding, how to really do this, because these are very special infinite length trajectories in time, which are not topologically, they're very nice, but they're kind of hard to compute, because when you have an unstable system, computing something for infinite time makes it rather hard to do it well. So in practice, this is a very good guide about how neighborhoods are connected. But we find periodic orbits much better. Periodic orbits have a property that never slow down, because if periodic orbit ever developed velocity zero, it wouldn't be periodic orbit, it would be a heteroclinic connection, because that's the definition of heteroclinic connection. It's something, a curve that goes to equilibrium, because at equilibrium there is velocity zero. And periodic orbits, by definition, have monotonely non-zero velocity every place. So these ones are actually much better guides to neighborhoods, because what they do is they zoom through a set of neighborhoods without ever stopping. So we take a tour and we come back. And so, this is the deep idea, but we don't really know how to implement it as computation. Well, as I'll show you, exploring things by dynamical invariant sets like periodic orbits will be very good. So now I've told you, if you have your dynamical system, I told you first, define equilibria, and to do this you have to slice Poincare section, etc. So all that other stuff was technology, how you do it. And now we have a set of points which are either not moving or they're mapping in a nice way as periodic orbits map. So they're morally fixed points, but they're permuting sets of fixed points. That was step number one. Then I told you, okay, the neighborhood, you compute the linear neighborhood. No problem, it's just a matrix, eigenvalues, eigenvectors. And now I'm telling you, now we can go global and connect everybody who is connected. So there is a technical term saying that there is a set of neighborhoods in which dynamic is transitive, meaning that from every neighborhood you can get to any other one. If you are world unto your own and Mars, they have different neighborhoods, it doesn't matter, you're analyzing only connected sets. So that's what we will try to do. And the next step I'm a little bit unhappy about, and you'll never appreciate what is this obsession. The next step is I will now start measuring distances along these curves. And to measure a distance, you need a metric. Now, in special and general relativity, you have very good reason to have metrics, because our world is Euclidean, and or Minkowski, more correctly, and the way the general relativity is put together, they're on a manifold where the local neighborhood is Minkowski, but the global one is like this. It's some curves, curvilinear surfaces. And that's very good physics. But if you're looking at chicken hearts beating and you describe them as partial differential equation with 17,000 coefficients, it's not obvious what the distance is between objects in 17,000 coefficients. I mean, I can just say it's Euclidean distance, but why? Because if I choose some other discretization, I'll get different distance. So the metric makes me unhappy, but I don't know at the moment how to avoid it. So let me explain how the measurement goes. And the reason why we need to do this measurement is because I told you already in a very simple case that if we measure unstable manifolds, we can get extremely simple dynamics on recurrent, Poincare recurrence return maps. But I didn't tell you in detail how to do this. So if I'm on this manifold, locally this is a smooth curve. So I can define Euclidean length, for example, ds square for this interval, ith interval, to be the sum of a equals 1 to dimension of the space dxa square, and this is a vector, these are components of the vector. In other words, locally I can look at a tangent to this curve, and that's a little vector called dx, which is not 3 but zillion dimensional, the full dimension of the space. And I can define the distance on the curve. On every one-dimensional curve I can define a distance like that. But maybe there are other representations in which the distance is defined in a way that, for example, depends where I'm in a state space. And this is a symmetric matrix. The moment you do this, it looks totally natural to us because we're used to living in Euclidean worlds. The moment you do this, you've changed everything because your dynamics now has a notion of length. And for example, you do not know whether this length is invariant under coordinate transformations you had before. Before you had a huge symmetry of group transformations because everything was allowed as long as the conjugacy was smooth and these invariant properties were preserved. But now I want to preserve length, and I don't know why I want to do this. But ignoring this remark, if you can just ignore it, it now enables me to put coordinates on my unstable manifold. So it's not just any curve, but I can actually measure distance along it. So I can start here measuring my distance, and when I come to here, this is a one parameter, which is curvilinear distance. Which is simply on the ith interval, let's say beginning of ith interval, S of I is just the sum, square root of the sum of these little lengths. And when you think of it, it has to be this way because it's nonlinear dynamics. So there are no planes and lines. Everything is nonlinear. Everything is curved. And if you're going to have some distance, you want to measure it along these curves. And it becomes very obvious when you start seeing what this unstable manifold does. What it does is once it hits an obstacle and starts going back, it can be very close in a global distance. So if you're not careful, you might think that these 2 points, because you look at them, and they look very close. But actually miles away on the unstable manifold. On this curve, they're very far. So you really need to start measuring distances in intrinsic coordinates for your system and not some random externally imposed discretization of the space. And now if you do this, wonderful things happen, which really impressed me because it's obvious when you do this on Rossler attractor. And what's the big deal? 3 dimensions, Poincaré section is 2-dimensional. The thing looks like a curve. You measure this distance. If everybody is on this curve, you just see how they move on the curve, and you discover a 1-dimensional map describes everything in 3 dimensions. And in this week's problem set, you look at some really messy thing because you have continuous symmetry, and eventually you get this 1-dimensional map. It describes all the invariant solutions, and then you can just plot them in a big space. It's 1-to-1, and it's great. But it actually works for high-dimensional space. That's totally surprising. So it works for fluttering flame front. It works for Navier-Stokes. So what happens, there are interesting recurrences in these systems as well. And even though in huge dimensions you can draw these lines, you can measure the distances, you can take your solutions, they're 100,000 dimensional, but on these lines they're very low dimensional. and you can start mapping them out. So I find that totally amazing and pleasing. And I'll give you a little example, which is connection. So last example I gave you was three-disc pinball game. And problem with that example is you understand it totally because you can either go left, right in every end.
We already had time as a parameter along the curve. What's the advantage of the distance?
The problem with time as a parameter is that time goes to minus infinity to plus infinity. But you might be right. You know, it might be a good parameter because it's built in, but after a while you get used to the idea that time is not sacred. You can redefine the time, and often it buys you a lot. So we didn't include it in the problem set this week, but there are some singular behaviors where your phase velocity speeds up a lot. If you rescale the notion of time by distance from the wall, suddenly everything is smooth. And same is true in celestial mechanics and atomic physics. Whenever you come close to a nucleus, you have to change your space resolution because you go very fast, or you can redefine the time and then you just go slowly through that neighborhood. So this is an example. Here the curvilinear distance is just distance, but time goes from minus to plus infinity.
We defined some metrics, but do we have any requirements for it?
Do we at the moment, it should be a non-singular and symmetric, and I don't have better thing, and it bothers me a lot. So what happens in applied math is that people use the freedom of the metric to improve computation. So there were, Ulam that I introduced last week is the father of American hydrogen bomb, and Sobolev, applied mathematician in Russia, is the father of Russian atomic bomb. And to do things that go bang, you have to deal with very many time scales, and you have to do he's applied mathematician, but you have to do calculations that go many orders of magnitude, because you want this thing to go like that. And for that reason, he developed something called Sobolev norms. So he developed norms which are specially suited to calculations when you go very fast to something and come out, etc. So, but they're kind of art. I mean, you look at your problem and you say this Sobolev norm, which, for example, suppresses high Fourier modes. So it gives lots of weight to slowly changing things, but suppresses things like that. This one is good for me because my calculation works well enough. So it's used all the time. But as physicists, we are unhappy because we don't have a criterion for it. It just turns out if you divide by wave number squared, it looks better than if you divide by something else in the diagonal sum. So I think you should be aware that you're using norms without thinking because we're so used to Euclidean notion of length, we just put it on anything. But if you're comparing two photographs and you're looking at pixel distances, it's not obvious at all that you should be taking squares of differences of pixels. What you actually have to do is you have to go to Fourier space or Weber space and then measure the distance and do transform back when you think about it. But that's the engineering problem. We would like to have I would like to study this Navier-Stokes equation that says there is a distance that makes sense. And I don't have that. But it's easy to ignore this until you really have to think about it because it's so automatic for us. So here is a beautiful example how stable and unstable manifolds work, which sort of completes our three-disk billiard example. So there is Marcel Henon, trying to understand Pommeau, who is trying to understand Lorentz's model. And he says, well, the essential feature of what you're telling me is stretching and kneading. So what I need to say is that if I have a piece of dough, I would like to have dynamics that first stretches it, and then the baker folds it in some way. And then I have it on a table and I repeat this operation. So that's what kneading is. And that seemed to be, when you look at Lorentz attractor and Rosslea attractor, that's essential feature. What happens is that neighboring, if you start with a volume of points, the neighboring points get stretched along unstable direction and get really squinched along the stable directions. And then they come back where you started because, you know, it's recurrent dynamics, and then you stretch and fold. So that seems to be the main idea. Now, you know, what is it that stretches? So stretching means that I take some distance, some length, and I multiply it by some number, ax. And if a is larger in magnitude than 1, then I'm stretching. And what is folding? You know, I would like to take something, and I would like, if I square it, so this is a negative part, and this is positive. Numbers on this side are positive. When I square it, they both give me the same answer. They both map like that. So I would like to square, that will fold, and then I would like to do something with this. So I would like to center it someplace, let's say. So you stare at this idea. It says it's a nonlinear process. First nonlinearity is square, which is called parabola. From one-dimensional example, we know what it does. It stretches the interval and maps it in such a way that it gets folded forward in time, etc. So finally, he writes two equations, which I will no doubt write wrongly. So this is x and y. And the first one has a parameter a, and again, these equations will be wrong the way I'm writing them because I don't exactly remember it right now. And the second equation is b times so the correct equations are in the book, but the idea of Henon's model is that this A captures the stretching. So there's a parameter which where it's large. You know, this A could be 3, could be 6, could be something, but it's large. It means you stretch the thing. And then there's another parameter, and that parameter turns out when you compute Jacobian, this is 2 by 2 map, when you compute Jacobian, this parameter turns out to be minus the Jacobian. And what is Jacobian? Jacobian, it tells you how volumes change. So this parameter is the volume contraction of this original piece of red, and this one is measuring how far it goes. So that's the essence of a non-map. And now you go back and please read the book on this one, but what happens is that map is that if you take a fixed point someplace and you look at its unstable and stable manifold, you think about it and you discover you don't have to look at the stuff that's outside. All right, so this is unstable, W unstable, and this is W stable. So it turns out that the border, the thing that I had before for this 3-disk problem, there are some edges of the strips. These are actually stable, unstable manifolds. And if you're outside of those manifolds, you're just being pushed away. So you will not stay there forever. So they're cookie cutters that take your door and says everything inside of that line has a chance of surviving for a long time. Everything outside doesn't. And then you extend them a little bit and do the same thing as we did before. But the manifolds come back, etc. And you start producing the same picture that we produced for the, sorry, it's someplace in here. This kind of Smale horseshoe picture before, where what happens with this map is the stretching is strong enough. After one stretching backward and forward, you have 4 regions. But now their borders are infinitely precisely defined because they're stable, unstable manifolds. And that's something you compute. So these are not random squares someplace. They don't care about how your initial volume was decided. So if you know these guys, you have the borders. And that's now immensely powerful because now you start counting all possible solutions of dynamics because they have to be within these borders. So this completes this topological way of thinking. And now it turns out the theory will require that we actually compute something, and it'll require we compute periodic orbits. So next time I will discuss how you find unstable periodic orbits. But all this machinery is needed to find them. You first have to know where to look for them, and then you have to know, do they exist or not? And then you have to nail them down. And doing it blindly is a very painful process, but this is systematic hierarchic way of producing longer and longer orbits, as many as you need.